Today we're starting our 1-week unit on modeling, which basically means we're going to take all the functions that we've learned about this year and we're going to use them to describe some real-life activities and some real-life data. You've got your packet, and we're going to be working through the first activity together, just so you know exactly what I'm expecting, because I'm going to be grading these, and I'm going to be looking for certain details. So I want you to make sure you pay attention to that. If you open to pages 2 and 3, I've got some sort of reference guides that I'm going to be looking at. Page 2 has everything you need to know about how to use your calculator. So I'm going to suggest that you don't try to follow along with your own calculator on this activity. Just try to watch and think about what you're seeing, just so you'll be able to figure it out. So we're going to start with an activity where we measure our height in inches, and we measure the length of our fingertips from tip to tip, and that's typically called wingspan, even though it's arm span. So what I did is I made my x values stand for the height of a person in inches, and my y values are the wingspan of a person in inches. And I've always heard that these are supposed to be kind of close to equal if you're well proportioned, but all right, so the first thing I did was I went, stat is the button of the day. I went to stat, edit, and I got all those numbers entered into my calculator. That would be the first thing you'll need to do once you've collected your data. Ignore this. What we want to do now is we entered the data into our calculator. We're going to make a scatter plot, and we've never done that in this class, but maybe you've done it before. It's a way to have your calculator make the scatter plot for you. So let me show you how you'd set that up. Right here by the Y button, it says stat plot. So we're going to go to second, Y equals. And right now it says that my stat plot is off. So I'm just going to hit enter. And this allows me to set up my scatter plot. So I'll push enter to turn it on. And typically it's set up the way that I like it. It has a scatter plot highlighted. It's finding my x values and my y values in list 1 and list 2, and I like it to have those nice big squares. So that's how we would turn on our stat plot. The next thing we need to do is make sure that our window is going to be showing the right values. And you know that we had numbers in the 60s and 70s, so this isn't going to cut it. Our x value stood for height, and I think we had heights between maybe 60 and 80. So you'd enter your min and your max. X scale just means how often do you want a tick mark. So maybe every 5 inches I'll put a tick mark. My y values were wingspan, and those were, like I said, pretty close to the height numbers. So my min and my max would be 60 and 80 on that too, and I'll put tick marks every 5. Ignore the X res. The idea here is if you can get your window set up, when you hit the graph button, you should see a scatter plot. And that's what we're going for, because on your paper, I'm going to want you to just sort of sketch what you see. Something like that. Now the things that I need you to label is I want to see what you chose for your window. So if you would put your X min and X max, your Y min and Y max, and then the other thing I need to see is I need to see like a wording label for what do X values even stand for. X values stand for height on this one in inches, and our Y values stood for wingspan in inches. And you can go ahead and copy this stuff down just so you have this to look back on. So we've indicated our window values, that's the 60s and 80s. Sketch the scatter plot and label the axes. That's what we're looking at. Based on the scatter plot, which type of function do you think models this situation best? And since I was sort of expecting that all the values would be equal, I was thinking that it was going to be linear. So it looks sort of linear. So that's my hunch, is that it's going to be a linear sort of fit. Once I've decided on that, I'm going to run the regression, and that just means find out what equation, what y equals mx plus b works. Again, the button is stat, this time calc. We've done this before. And we're going to go to linreg. Now that's what I had up here before. Your calculator is going to look a little different. Your calculator is going to look like this. My old school calculator on my whiteboard looks like this. So I have to type this stuff in manually, but the default is list 1 and list 2 for your x and y. You can ignore this, but the store regression equation, that's what I really want to make sure we do, because it says storing the function as y1. And so let me show you how to get there. So on my calculator, I have to type in the list 1 and the list 2. Yours should be set up for that already. Now you're going to have to type in the y1. And there's directions on page 2 to show you this, but just so you've seen it before, the button to find your y variables is this variables button. So we're going to go to variables, arrow over to y variables. It's under function, and we can use any y value we want, and I wanted this as y1. So once we have that, you'll click on calculate, I'll push enter. Before I started, I turned on my diagnostics. Remember, that's under your catalog. There's directions on page 2, so you make sure you can see your r values. But here's what I have. I've got my y equals mx plus b ready to go. The type of regression I ran was a linear regression. When you write down the equation, this applies to the whole packet, I want you to round to 2 decimal places. So copy this down, 1.15x minus 10.41. So that's what I'd want to see is 2 decimal places. And this one's y equals mx plus b, since it's linear. We're going to just always go with the the r squared, because not every regression shows a regular r value. So we're always going to go with r squared. So we've got our line ready to go. If we go to our y value, you can see that it's already entered our equation for our line. And if we go to our graph, not bad, right? And remember, the closer that coefficient is to 1, the better the fit. So now we have to try to think of another type of regression. So that's where page 3 comes in handy in your packet. Page 3 shows all the functions that we've talked about this year. So we talked about linear. Parabolas don't always have to look like U's. It could just look like 1/2 of a parabola. That would be a candidate for a quadratic regression. Cubic is nice to use if you have a couple of turning points, but a cubic would also work if you just had sort of this part of the graph. So a cubic could fit to a quadratic pretty well too. There's no wrong or right answer for which one you choose. If you have a graph that's sort of looking like this shape, maybe that's a logarithmic graph. Just know that you have to go to the ln regression instead of the log regression. Our calculator doesn't have that. Another thing to remember is that exponential equations can either be growth or decay. So if you see a shape like that, exponential might be right for you. These 3 I want to talk about because these all fall under the power regression. And the reason for that is because anytime you have an x to a number, that's a power model, a power parent function. And a square root is like an x to the 1/2, and a cube root is like an x to the 1/3. In rational functions, it was a while ago, like 1 over x, that's x to the -1. So anytime you have a hunch that it has a shape sort of like one of these, you would want to use the power regression. If you think it might be looking like a sine or a cosine curve, you're going to use sine regression. It doesn't have a cosine regression, but it'll make it work. So now I have to decide what else do I think this could look like. I don't even really know, but to me, maybe it looks sort of curved like that. So maybe it's I'll pick square root. So remember, if I think it's a square root, I'm going to have to go with a power model, a power regression, because that's like x to the 1/2. So let's try this one. Under stat, calc, I have to go down to find my power regression. Oh, apparently I should have gone up. There's my power regression. Your screen is again going to look your screen is going to look a little different because it'll tell you where you want to store it. So when I do this, I'm going to have to type in my list 1, list 2 manually. And then if you see under the directions, it wants you to store this one as y2. So you're going to have to find right here, you're going to type in y2. y2 is found in the same place. We're going to go to vars, yvars, function, but this time I'm going to store my second one as y2. Let's give the equation. So you'll see at the top it says y equals a times x to the b, and it's giving us an a and a b value. Y equals 0.52 times x to the 1.16, two decimal places. And my coefficient of determination, I'm always going with y squared, is 0.88. Now this one's actually a little higher because remember I had to round this up from 0.87 something. So this one's actually a little bit higher, which technically means that this is a better fit. Again, it's stored both of those now. I put my power model into the second one, and when I look at the graph, the line will come first, and the power model comes second, and you can barely even see a difference. They were both a pretty good fit. They were both right up in the 0.88. By the way, I was totally wrong thinking that this would be a square root model. It didn't have a power of x to the 1/2 at all. It was actually over 1. So it's going to choose what's best for our data. So now I'm going to look at the graph and decide which type of model I want to use. Now, there's barely even a recognizable difference. So I think I'm just going to go with my gut. I thought it was going to be a linear relationship because I thought that, you know, the heights and the wingspans were going to be equal, and if they were all equal, that would have been a perfectly straight line. So I'm going to go with linear. That's what I'm going to choose. Does my choice, does the coefficient of determination support my choice? And it actually doesn't. It doesn't, because remember I had to round this one up. So this one's actually a little lower than this. So I'm gonna fess up. I'm gonna say no. The power model had a higher r squared. And that's totally fine to go against the numbers, because I thought that this was a linear relationship, and honestly I think that was maybe just a fluke because of my data. Use your model equation. So when it says model equation, that means the one that we've chosen, and I chose this one. So I'm going to use this equation to calculate the predicted wingspan of a 6-foot tall person. A 6-foot tall person, that's an x value. 6 feet tall people are 72 inches tall. So I'm going to use this equation. It says to show my work, so this would be showing my work. A 72-inch tall person. What would I expect their arms to be like? Oops. Pretty close, right? If you're 72 inches tall, maybe your arms are about 72 inches. That would be the predicted wingspan if I were 6 feet tall. I showed my work. How close is this to my table values? So then I'd go back to my table and see if I had a 72-inch tall person, and I did. And I'd compare, and this person actually had sort of longer arms than expected. So I'm just going to talk about that. So I would say that the actual data showed about arms about 2 inches longer. And I'm just going to explain that. How close is it to your table values? I'm going to be grading you just to, show me that you thought about it. What domain and range are realistic for this situation? Because this model might go from negative infinity to infinity, who knows? But what we want to talk about is what domain and range makes sense for heights and for wingspan. So for heights, I'm thinking you'd always be more than 0 inches tall. and maybe always under, I don't know, I don't have the Guinness book with me, but maybe 100 inches. And since the Y values are pretty close in this situation, I'm going to say the same range. I just got to check. Okay, so I said that my model might work up to an 80, what'd you say? Oh, 1,100 divided by 12. Yeah. So it goes up to like an 8 1/3 foot person. So I think that's a good enough domain and range. This is the type of thing I'm expecting for each of the 7 activities. We have every day this week to work on these. Remember to use pages 2 and 3 as a reference. Today, I'd like you to get started, and I think you can probably make it through the dog park activity. And if you have time, maybe you can start the second one about the popcorn box. But our goal is that by the end of the week, we'll be able to turn this in, and this will be your grade. Instead of a test, I'll be grading your packet. So work hard. You can work in groups of 2 or 3, but keep it between 2 and 3. I don't want anybody having a giant group. And you can get started. Everybody turns in their own packet, and if you have any questions, I'll be here tomorrow.